Let me welcome you to this lecture. We have been discussing the chemistry of group 14 elements, and we have so far looked at different types of allotropes of carbon, and we have also discussed the chemistry of two of these allotropes, that is graphite as well as of fullerene. So during this lecture we will discuss about another important class of compound formed by carbon, that is called the carbides. Now, carbon is one element which forms binary compound with all other elements in the periodic table, almost all other elements in the periodic table, and we have already looked at one carbide, that is at the chemistry of boron carbide. So the compounds of carbon with uh, less electronegative elements are essentially called the carbides. Now, in order to the attempts to classify the carbides on the basis of their structure as well as on the basis of the type of bonds formed by present in these carbides essentially fail as they fail in case of two other classes of compound, that is metal hydrides as well as in case of metal borides. We have discussed about metal borides earlier, and we have seen the kind of intricate structures in metal borides. Now the carbides are also the structures are very extensive nature of structure is present in case of the carbides, and the uh, these classes of compound, that is metal hydrides, metal borides, and metal carbides, they all show similar trend in properties, that is with the with electro positive metals they form polar compounds. So metal hydrides, metal borides, and metal carbides, they all with electropositive metals, they form ionic or polar compounds, while in case of electronegative non-metals, they form covalent compounds, and elements with elements in the middle of the block, they form something known as interstitial compounds. So we will discuss about two different types of carbides here, or essentially about ionic carbides and about interstitial carbides, while the covalent compounds or the compounds of carbon with electronegative non-metals, they will not be discussed, and they form covalent bond with carbon, and we do not classify these molecules or these compounds as carbides indeed. So let us discuss about ionic carbides to begin with. So as we have said that electropositive metals form these ionic carbides, and in these ionic carbides, carbon is present as anion, and the most simplest type of compound or ionic carbide contains individual carbon anions. So these type of carbides which contain individual carbon anions. So we have examples of this type of carbides, that is beryllium carbide as well as Al4C3. This is uh, another carbide molecule which contain individual carbon anion, and these type of carbides, when they undergo hydrolysis reaction, when they come in contact with water, and both of these type of these carbides essentially result in formation of methane gas when they undergo hydrolysis. So these hydrolysis reactions are exothermic in nature, and in many times they are also explosive because the amount of heat release is very high, as well as the product that is formed is a flammable compound. So because when these carbides which contain individual carbon anions in their structure and they hydrolyze to give us some methane, so such carbides are also called methanides because they yield methane upon hydrolysis, and that is why they are called methanides. So apart from these carbides which contain individual carbon anions, there are also carbides where there are C2 units are present. So examples of such carbides, the alkali metals, they form such carbides which contain C2 units, and the formula of such carbides is M2C2 type the formula, because the alkali metals are one positive ions. So the formula of such carbides are going to be M2C2, and the preparation is quite straightforward. The preparation of this type of M2C2 type of alkali metal carbides are very straightforward. That is, one takes a metal and then react it with ethylene in liquid ammonia, using liquid ammonia as the solvent, and this essentially results the M2C2 type of metal carbides with alkali metal ions. So again, these carbides also undergo hydrolysis rapidly when they come in contact with water, and the product in this case, or when they undergo hydrolysis, the product in this case is acetylene, and that is why these carbides which contain C2 units, because they yield acetylene upon hydrolysis, they are also called acetylides. So other examples of acetylides we have with alkaline earth metals also. Such acetylides are known. So that is M2 positive. So MC2 is going to be the formula with alkaline earth metals, and good example is calcium carbide, which is a industrially important carbide, and we will discuss about the preparation as well as application of this carbide. So these carbides can be prepared in general by, again, reaction of the alkaline earth metal with ethylene at around 500 degrees Celsius. One can obtain C2 in this way. So that is how alkaline earth metal carbide containing C2 units or acetylides of alkaline earth metal can be prepared, and we have already said calcium carbide is the most important example of this type of carbide. And calcium carbide, because it is used as a source of acetylene gas, as again upon hydrolysis calcium carbide yields calcium hydroxide and acetylene in this way. So that is why calcium carbide is a good source of acetylene. So acetylene is also used in oxyacetylene flames. For that purpose also calcium carbide was initially, or earlier in earlier times, it was used as a source of acetylene. So the industrially calcium carbide is prepared by using a different procedure. This one takes lime, which is calcium oxide, and do reaction with coke, that is carbon, at around 2200 to 2250 degrees Celsius. So the reaction is endothermic in nature, and this essentially results calcium carbide and carbon monoxide. And the enthalpy of this reaction, or the reaction enthalpy of this particular process, is 465 kilojoule per mole, and the reaction is endothermic in nature in this reaction. But then the hydrolysis of calcium carbide, as we have already seen, is exothermic in nature, and this reaction, the enthalpy of this reaction, minus 120 kilojoule per mole. So the reaction is exothermic here, and one must, during preparation of calcium carbide, one must control or the reaction in such a way that they know, or one must not expose the calcium carbide to water, or otherwise it will get converted into acetylene. So the calcium carbide is also a precursor for preparation of fertilizer, as calcium carbide can fix atmospheric nitrogen as it undergoes reaction with atmospheric nitrogen to give calcium cyanamide, that is calcium CN2, and carbon is also a byproduct in this reaction. So this particular reaction as calcium cyanamide, so what we have done here is that we have reacted calcium carbide with atmospheric nitrogen, and atmospheric nitrogen as such, it is highly unreactive in nature, and we know during the Haber's process for preparation of ammonia, one must apply very high temperature and pressure to fix essentially nitrogen into ammonia, and this is an alternate procedure where one can fix atmospheric nitrogen with calcium carbide to give calcium cyanamide, which is again used as a fertilizer, and this reaction is done at around 1100 to 1200 degree Celsius at a much lower temperature than the Haber's process. So this is another application of calcium carbide, as it can fix atmospheric nitrogen. So apart from methanides and acetylides, where individual carbon anions and C2 anions are present, we also have carbides where there is C3 4 negative ions are present, and if you count the number of electrons in this C3 4 negative ion and this N3 negative, that is ethyl ion, what we will find is that these two ions are essentially isoelectronic in nature, or the same number of electrons are present, and also we see that the same number of atoms are there, and that is why they are going to be isostructural as well. So the C3 4 negative ion is linear as the azide ion is also linear, we know. So there are examples of carbides containing C3 4 negative ion, and these are essentially Li4 C3, Mg2 C3. So these are the examples of uh, carbides containing C3 4 negative ions. So apart from ionic carbides, we also have interstitial carbides, which are formed by elements from the middle of the D block. And as the name suggests, these interstitial carbides are compounds or where the carbon atoms essentially lie in interstitial space of metals. So in interstitial carbon atoms occupy octahedral interstitial space in the lattice of metal. So these compounds or these interstitial carbides, their characteristic is that they are infusible, very hard, as well as they are refractory in nature. So their properties are quite similar to those of metal borides. What we see is that they are refractory, they are hard in nature, as well as they retain many characteristics of the parent metal, that is like the metallic luster is retained, as well as the conductivity is also retained in these interstitial carbides, and that is why these interstitial carbides are often used as in high-speed cutting tools. Say, for example, tungsten carbide or tantalum carbide. These carbides, because of their hard refractory nature, they are used in high-speed cutting tools, as because they are extremely hard in nature. Also, what we should notice is that because the carbon atoms occupy interstitial space in the metallic lattice, so the metal atom size of the size of the metal atoms must be large enough so that the interstitial space is also, or the size of the interstitial space is appropriate for accommodating a carbon atom, and the metallic radius or the threshold metallic radius for occupying or for accommodating a carbon atom in the interstitial space is equal to 135 picometer. So metals which have atomic radius of 135 picometer or above, they can form interstitial carbide because now the interstitial void is large enough to accommodate a carbon atom. So this essentially brings us to the end of this lecture. What we have learned during this lecture, or what we have discussed during this lecture, are about the metal carbides, and what we have seen is that we have ionic carbides as well as we have interstitial carbides, and ionic carbides are formed by electropositive metals of alkali. Examples are alkali metals as well as alkaline earth metals, and apart from the alkali and alkaline earth metals, lanthanides also form polar or ionic carbides, and we have seen that there are three different types of ionic carbides based on the kind of carbon anion that is present within the carbide. So we have carbides where individual carbon anions are present, and these carbides are classified as methanides because they yield methane gas upon hydrolysis. Then we have also carbides which contain C2 anions, and these carbides yield acetylene gas upon hydrolysis, and that is why they are termed as acetylides. And we have seen examples of alkali metal as well as alkaline earth metal carbides which form this sort of uh, acetylides. And we have discussed about the most important acetylide, that is calcium carbide, and we have looked at the industrial method of preparation of calcium carbide, which is by heating lime with coke at temperatures of around 2200 degree to 2250 degrees Celsius, which essentially results calcium carbide along with carbon monoxide, and this reaction is endothermic in nature. Then we have also learned that calcium carbide undergoes hydrolysis with water, and this reaction is exothermic in nature, and that is why this has to be controlled carefully during the preparation or during the manufacturing of calcium carbide. Then we have also looked at one of the important application of calcium carbide, that is because it can fix atmospheric nitrogen and it reacts with atmospheric nitrogen to form calcium cyanamide, which is an important fertilizer used in crops. So then we have looked at the interstitial carbides, which are essentially carbides where carbon atoms occupy the octahedral interstitial space of metallic lattice, and these interstitial carbides are non-reactive in nature. Unlike the ionic carbides, they do not react with water, and because they are also infusible, they're hard as well as they are refractory in nature. That is why they have found application in high-speed cutting tools. And then we have also looked at an important observation that the metallic radius for formation, or the threshold metallic radius for formation of interstitial carbide, must be equal to or more than 135 picometer, because otherwise the interstitial space is not large enough to accommodate the carbon atom inside the metallic lattice. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.